Hey there guys, welcome back to a brand new video. Today I am starting my new series on multivariate calculus and functions on the channel. So let me first introduce who I am. I am Cody Riley. I am currently studying towards a math major. I am currently going into my second semester in a couple of months. Currently finishing off the first semester, but with what's going on and lockdown, it's sort of complicated and it's sort of weird how things are going. And in terms of what you can expect from this particular series, we are going to be looking at things from looking at functions like so to triple integrals and some applications on those, and maybe even starting on partial differential equations later on in the series, of course, where after we sort of get an understanding of the integrals, etc., etc. So today we are just going to be doing some simple stuff. We're going to be taking some derivatives. We're just going to be looking at some functions here, and we're just going to introduce ourselves or recap on some multivariate concepts. So this is assuming that you have some knowledge and you've gone to university a bit and you're just looking for some recaps material. I wouldn't trust me just yet on teaching the complete syllabus of your course. I'm just here for revision. Okay, so let's start on looking at simple multivariate functions. So here's a statement here. A variate function is defined by some function having some vector put into it and giving an exact output. So an n vector, so it has n components. And we can write this as x1, x2, right up to xn. And it could be R2. R2 would give us a vector x1, x2. And this is what we'll be using quite a bit. So for example, xy is an R2 vector, and R3 is xyz. Usually you use xyz and xy. Fourth dimensional functions aren't really used in applied mathematics. You can use them a lot in economics, I believe. So let's just recap. If we have some vector that has n inputs and we put it through a function, so we put this thing through a function f, it will then give z, which is a one-dimensional output. So let's go ahead and do some examples. So let's say we have a function defined by the vector x is equal to xy minus xy squared is equal to z. So z is equal to this function. So first of all, let's identify what our vector is. Well, the variables that we have on the right-hand side is x and y. So that would mean we have an x and a y vector. And that means we have a vector in R2. So we can say that we have some vector going through a function and giving us out an output in R1. Okay? And that is normal for a function that we evaluate. Otherwise, you either get a vector or you can get a matrix, which is a linear algebra concept, which I might do another series on later on. So let's go ahead and let's take these vectors and see what they are. So in this case, x1 would be 1, 1, and we're plugging it through the function. So we go plug it through the function x1, and that is f of 1, 1. And we pop those into the substitution. So x is equal to 1, y is equal to 1, x is equal to 1, y is equal to 1. So we get 1 times 1, take away 1 times 1 squared, and we get a result of 0. And if we look at x2 is equal to 2, 1, we get f of x2 is equal to f of 2, 1 is equal to 2 times 1 minus 2 times 1 squared. And again, this gives 0. And of course we have x3 that is equal to 0, 1. That is put through the same function again. And in this result, we also get 0. So it looks like we have a relation here. These points all go to 0. The height of the function at these points is 0. And let's say for a second, let's say we had some vector that is not defined here, x, y, z, and that is plugged into f. Well, technically, let's use a different variable actually. We have a z that is equal to, let's use p. Well, it doesn't really matter because we have 3 inputs here, x, y, p, and by the definition of laws of vectors, the first thing you look at is your x, your y, your p. We have no p's here, so any value that is real in the p slot will not be mapped to the function. So strictly we have 2 variables, so we only can have a vector of 2. So nope, that will not work at all for all p. For all p that is real, this will not be mapped. Will not be mapped. Okay, so let's consider this other function defined by another vector going in. Okay, we have 3 variables in this case. Okay, so we can assume that A is going to be a vector with 3 variables. If it wasn't, then would be limited to only putting x and y in. Okay, so in this case, A would be equal to x, y, z. Unlike this one, z was our output. And let's call this function, let's say we put A through the function and we get a real output, which we will call B. Now these types of problems are hard to imagine in the human mind just because they're more than 3 dimensions. It's a 4-dimension question because we have a sole point going in. What's coming out, who knows? Geometrically, we are not too sure about this. So let's go ahead and let's put in the points here. 1, 2, 1. And we get 1 multiplied by 2 multiplied by 1. That would equal 2. And let's say we have the vector 1, 0, 0. Here we would get 1 times 0 times 0. And let's just do an extra problem here. Let's say I have a vector p that is equal to 1a, 1a0. Q is equal to a0, 1. And t is equal to 0, 1, a. So what I've done here is I've moved the zeros and some of the numbers around. And let's see how that impacts the function's value. For some reason I put f's here. I think it's just standard just to use f's. So that's supposed to be g's. We're putting it into this function. We still use the same function, so the answer is correct. So we put in the vector p into g, and we get 1 multiplied by a multiplied by 0, so we get 0. If we put q into this function, we get a multiplied by 0 multiplied by 1, which is 0. and g with the vector t is equal to 0 multiplied by 1 multiplied by a, which is equal to 0. So if one of the components of the vector is 0, one of the points, then we would have a resulting output of 0 for any other number. So for example, if we had the x is equal to 0, then that sets the point. It's automatically 0 for every other variable being inputted. Alright, so let's go ahead and let's move on. Let's move on to partial derivatives. So the change of multivariate functions is very similar to the change of functions in two dimensions. For example, f of x, we looked at the change of x in respect to y. So for example, if we were looking at a parabola, we were just looking at the slope of the tangent. The slope of the tangent line, I should say. The partial derivative, you can look at the slope of the tangent in a particular direction, but we can furthermore develop this into the concept of looking at the slope of the tangent vector and the tangent plane, which we will look into in the later videos. So what's an example we can look at? Let's look at a surface defined by some function of xy. And let's try and draw some axes right here. If we draw some axes, we have different directions, z, x, and y. So let's say I was interested in looking at the partial derivative, the rate of change in the direction of y. So all we would have to do is we'd have to restrict ourselves to the y-axis. So what does this mean? Well, we have a choice of values for x. What do I mean by this? We have a change in z. No, z is our function. Z is what we're mapping these two components to, I should say. And if we're looking at a particular change in one direction, then what we can do is we look at z is equal to f of x naught y, if we were looking in the y direction. In the y direction. And if we were looking in the x direction, then we would make y a constant. And how that works is we use the level curves to approximate a tangent line, and we can use directional vectors to find a tangent plane, which we will do in the next video. But for now, let's find some partial derivatives. So here we'll find the partial derivative of f of xy is equal to x squared y minus y squared x in both the x and the y direction. So it's really hard to actually draw a function like this, so we can't really look at a drawing unless I bring up a sketch, but let's just do some algebra in this video, and we'll show some geometry in the next video. So, and I'll link that below as well. So let's look at the partial. So the partial is actually a curly d over the curly d in what direction? So we'll look at the x direction first for alphabetical order. And what are we looking at? We're looking at f, but we have f is equal to x squared y minus y squared x. So we can pop x squared y minus y squared x in here directly. And recall that we make y a constant. So we can go d dx. Yes, we have made it into a standard derivative of x squared y naught minus y naught squared x. So now it's just a normal derivative. So that is equal to 2x y naught minus y naught squared. And if you really want to, it doesn't really matter if you do or not, but you can simplify out a y naught. That can help with finding critical points for anything, even if you're looking in one-dimensional, at two-dimensional, or even three-dimensional functions. And now let's find the rate of change in the y direction. So the same function, only this time we are holding x constant. So we go d dy of x naught squared y minus y squared x naught. So we do the same as we would do in the earlier particular functions and looking at standard derivatives. So we get x naught squared minus 2yx naught. And that is our derivative. Awesome. So let's go ahead and move on to the next example here. Find the derivative of the function defined by g of xy is equal to natural log of xy minus 2xy. And both the x and y direction, of course. So this is going to be very similar to one another, solely because they have same degree polynomial inputs and no products. So let's go ahead and do that. So we find the partial of x first for the function of the natural log of xy minus 2xy, and that is actually equal to the partial derivative of the partial of x of the natural log of xy minus the partial of x of 2xy. So we've moved the negative out front here. And here, again, we set y to a constant. So we get d dx of the natural log of xy naught. Take away d dx of 2xy naught. And here we use the chain rule. We go 1 over x y naught multiplied by the derivative of the bottom function only in respect to x still, and that is y naught, subtracting the derivative of this as well, which is 2y naught. And that simplifies to give us 1 over x minus 2y naught. Okay? And that's in the x direction. So for the y direction, we do the same, but we put x as a constant. So x as a constant. So we only take the derivative in respect to y of the natural log of x naught y, take away d dy of 2x naught y. So we're setting x to a particular point on its axis. And here, by the chain rule, we get 1 over y x naught multiplied by x naught again, subtracting 2y. Sorry, that's my bad. 2x naught. Okay? And of course that simplifies to 1 over y minus 2x naught. So that's all the problems for today. Let's see if we've made any errors and correct them. Nope. So in conclusion, for partial derivatives, we look in particular directions. We set other directions to a constant number. Why? It's so we restrict to a level curve and we find the tangent line or the rate of change of that particular level curve. So when finding the rate of change in a particular direction, x or y, for a three-dimensional function, z is equal to f of xy, you're finding the rate of change of a level curve. Okay? So that is the end of this video. In the next video, we'll expand more, do some more examples. I'll see you there.